Chapter 7, The Fires of Nuclear Fission, Part 2. In this lecture, we're going to look more at what is radioactivity and discuss how radioactivity could affect you. First, let's talk a little about natural radiation. Now, these units here, sieverts, or more specifically millisieverts, we'll talk about later on. But for now, you could see this as just a numerical magnitude associated with radiation exposure. So a 7-hour airplane flight would give you a radiation exposure of 0.05 millisieverts, while a chest x-ray would give you 0.04. So a chest x-ray is about equivalent to a 7-hour flight. The net total for a domestic airline pilot is somewhere around 2 millisieverts a year. We actually have radionucleotides in our body, the most common being potassium, and that actually gains us an exposure of 0.26 millisieverts a year. There's radiation from the sun that gives us about 1 millisieverts per year. And then there's also inhaled radionucleotides, 0.01 millisieverts per year, from natural deposits of radiation. We can get about 0.26 millisieverts per year, which can be greater depending on the amount of radon in your home. That can be significantly larger. There are also cosmic generated radioactive particles, and some of those make it through our atmosphere, and we get 0.28 millisieverts a year from those. In space, without projection of the atmosphere, there is the radiation exposure of about 27 millisieverts per year if you were in a space station. So you get much more radiation in a space station than you do on planet Earth. So an example of radiation dosage, just to give you an idea, due to the potassium content of bananas, you can get 0.1 microsievert. So remember, a micro unit is 100 times less than a milli unit. So just a super, super tiny amount from eating a banana. And then there's just a very small amount natural radiation in the human body. And that compared to a dental x-ray, which is 5 microsieverts or 0.05 millisieverts. You can see that this is much more. The extra dose per day in a town near the Fukushima plant, the recent nuclear accident, that's quite significant. 3.5 microsieverts. It's almost like having an x-ray, dental x-ray, every other day. So I don't think I'd want to live in this particular town. I imagine there's no longer large population densities in these towns. Most people have probably moved out of those areas. This pie chart shows the various radiation exposures that most people would have in the United States. 50% of the pie comes from radon, and again, that could be somewhat larger or significantly larger depending on the radon deposits near your home. And the other exposures to X-rays, we've got terrestrial radiation, internal radiation, cosmic radiation. Those are all very similar, almost evenly divided. A little from consumer products, but definitely X-rays, 10% of your total radiation exposure. That's something you want to consider in terms of how many X-rays you have a year. Please watch the following videos to provide a foundation in the understanding of radiation. So just a summary, you learned about the alpha particle, which is represented with a helium isotopic symbol or a little Greek alpha symbol. There are 2 protons, 2 neutrons, and it has a 2+ charge. So it's not exactly like a helium atom, which we'd assume to be neutral. It's actually a helium atom missing its 2 electrons. So that's why this little alpha symbol is perhaps a little more accurate. But when something undergoes alpha decay, the mass number will decrease by 4 and the atomic number by 2. Beta decay is where you lose a beta particle, represented with an electron symbol. It has essentially 0 mass, relatively speaking, since it's so light compared to a proton or a neutron, and has a charge of -1. When you have beta decay, the mass number doesn't change, but the atomic number increases by 1. And so what it is believed is that what essentially happens during beta decay is a neutron is converted to a proton. But since a proton is positively charged, and to have something neutral turn into something positively charged, you essentially, to have balance, you must also have the release of something that's negatively charged, and that's our beta particle. Then we have gamma emission, and that's essentially just a gamma ray, or we can consider that a particle or a packet of electromagnetic radiation being emitted. There's no change in the mass or the atomic number. This is how, if there is a slight loss in mass, some of this energy would be released in the form of gamma radiation. Now, when something undergoes radioactive decay, very frequently it will continue to decay until it becomes a stable isotope. So all the different isotopes something becomes within the decay process is known as a decay series. So here we have a decay series for uranium-238. You can see on the x-axis we have protons numbering from 78 to 92. On the y-axis, neutrons 122 to 148. Initially, uranium undergoes beta decay to become thorium-234. And then thorium undergoes a series of decay to become uranium-234, one of which would be beta decay. And so on and so forth. It keeps decaying and decaying and decaying and decaying, undergoing different types of decay until you reach lead-206. Lead being a relatively stable isotope. It still can undergo decay, but this form of lead-206 is relatively stable. So, and also, you also want to notice here that alpha decay is the left arrow, the red arrow, and beta decay is the right blue arrow. Anything with an atomic number 84 or higher are radioactive to some degree, some more so than others, but there's something fundamental about very large nuclei that make them somewhat unstable. Thinker Buddy. Strontium-90 is a radioactive fission product that contaminated milk in parts of Eastern Europe for some time after the accident at Chernobyl. This radioisotope is one of the products formed if a neutron bombards a uranium-235 nucleus. 3 other neutrons are produced as well as another element. What is that element? A. Antimony with the symbol Sb. B. Plutonium with the symbol Pu. C. Thorium with the symbol Th. Or D. Xenon with the symbol Xe. You may need your periodic table to answer this question. D. Xenon is the correct answer. And this is how we solved it. We needed to look up the atomic number of strontium. So strontium has 38 protons. If uranium split into 2 different atoms and strontium was one of them, then the other one had to have 92 minus 38, or 54 protons. The only element in that lineup that had 54 protons was xenon. And all elements that have 54 protons are xenon. On average, the largest contributor to background or natural radiation in the U.S. from human-made sources is A. Consumer products, such as smoke detectors, B. Occupational exposure while mining uranium, C. X-rays used for medicinal purposes, or D. Radiation escaping from nuclear power plants. C is correct. X-rays are one of the largest contributors to our natural or background radiation sources. Perhaps natural is not the best word. But consumer products, very little, maybe 3%. Obviously, we don't all mine uranium, so if we're talking about on average for the average individual, that's not really an acceptable response. And D, radiation escaping from nuclear power plants. Yes, if you're living near the zone of a nuclear accident, perhaps there would be more radiation, but if you're near a nuclear power plant that's running efficiently and safely, the exposure to radiation is essentially very little compared to what you would get for X-rays from medicinal purposes or even from natural sources like cosmic rays that penetrate the atmosphere. So ionizing radiation is radiation that has a certain energy associated with it. So you see here the frequency as well as the wavelengths. So it's electromagnetic radiation with very short wavelengths that's high enough in energy to actually knock electrons off or ionize molecules. So that's X-rays and gamma rays. Like we mentioned in previous lectures, those are our very high energy electromagnetic radiation. And if we're talking about radioactivity, we usually refer to those as ionizing radiation. Alpha and beta particles, as well as gamma and X-rays, are ionizing radiation. The problem with this type of electromagnetic radiation, or these radioactive particles, they can form highly reactive free radicals with unpaired electrons. So if you have a water molecule and you knock off an electron, all of a sudden you've got this unpaired electron, which is very unstable. Rapidly dividing cells in the human body are particularly susceptible to damage by free radicals. So this could cause cancer, which is one of the biggest problems with chronic radiation exposure in particular. Ionizing radiation can also damage healthy cells, and if you have acute radiation exposure, meaning a high dose of radiation in a short period of time, you can get burned. You can have radiation burns, so damage of cells. It can also damage cells internally, and you can get very, very sick. Please take a look at a video on radiation units. So I like this analogy for the units of radioactivity. So first we start with the number of disintegrations per second. How many atoms undergo decay per second? It's like all the apples falling from a tree. But the number of apples that can actually hit the sleeper is compared to the gray, or the absorbed dose. And then the effect on the body is dependent on the size or weight of the apple. That can be compared to the sievert, or the effective dose. So there's many different things that we need to take into account when looking at radioactivity. So again, the becquerel is the SI unit, the System International, the internationally accepted unit, and it's abbreviated BQ, and that is equivalent to 1 disintegration per second. And disintegration per second is often abbreviated DPS. And the Curie is a unit to express very large numbers of disintegrations per second. Instead of having something like 3.7 times 10 to the 10th becquerels, we say, okay, that value is 1 Curie. And the Curie was designed based on the number of disintegrations per second from 1 gram of radium. And of course, after the famous Nobel Prize winning chemist Marie Curie, who won 2 Nobel Prizes for her work. Let's take a look at an example of a decay. What do I mean by a decay? So in this example, we see 1 disintegration. If we only have that 1 decay or that 1 disintegration happen in 1 second, it would be 1 becquerel. So the absorbed dose is the energy imparted by radiation onto absorbing material. So we represent this in the gray. So a gray is 1 joule per kilogram. And 1 gray is equal to 100 rads. So this is another unit of measurement of energy that can be absorbed. So we want to take that into account along with the dose equivalent. So often we use REMS to indicate the dose equivalent, and what that means is we need to take into account the type of radiation. So the REMS, how many REMS you're exposed to, is the rads, which isn't an internationally accepted unit. The internationally accepted unit is the gray. This would be 0.1 grays times the quality factor. Q equals 1 for beta particles and gamma and X-rays, and it equals 10 for alpha particles. So our sievert then is basically the internationally accepted unit for radiation dosage. Again, REM and rads, that's US units, so you'll see that a lot in the US. That's why I wanted to review it. But really, sievert is how we discuss radiation exposure, take into account the type of radiation and the energy that can be absorbed, all in one nice unit. So this just summarizes the physiological effects. So here's sieverts versus REMS. Okay, so the difference is just really the order of magnitude. Small dosage like we would get in background, or aka natural radiation, there's no observable effect. Larger doses, we see a white blood cell count decrease, and then more and more radiation, we see more and more horrific impacts. And of course, if you get a very large amount of radiation in a short period of time, you will die. This ends Chapter 7, Part 2.